Hello everyone, hope you are doing very well. So today we are going to discuss the JEE PYQs of chapter Haloalkanes and Haloarenes. So let's begin today's topic, NCERT chapter 6, Haloalkanes and Haloarenes, JEE previous year questions. This is disclaimer. So let's begin with our first question. Question asking that correct statement regarding nucleophilic substitution reaction in a chiral alkyl halide is. So regarding the nucleophilic substitution reaction shown by chiral alkyl halide, you have to choose the correct statement from the given options. Options are retention occurs in the SN1 reaction and inversion occurs in SN2 reaction. Racemization occurs in SN1 reaction and retention occurs in SN2 reaction. Racemization occurs in both SN1 and SN2 reactions, or racemization occurs in SN1 reaction and inversion occurs in SN2 reaction. So for this question, the correct answer is option D. Let's understand the different nucleophilic substitution reaction shown by alkyl halide, in which the first is substitution nucleophilic unimolecular reaction. The SN1 reaction is a two-step reaction. That means it includes two steps, where the first step is a formation of carbocation and it is a slower step. It is a radiator-remaining step. So reaction will proceed via formation of carbocation. SN1 reactions are accompanied by racemization factor. So in the SN1 reaction, racemization happens. How? So we will see that. Why the racemization occurs? What is the reason? The carbocation intermediate form in the SN1 reaction in the first step, which is the slow step, is sp2 hybridized, and also the carbocation is planar. That means achiral in the nature. And due to this, the nucleophile attacking on the carbocation can attack from either side of the planar carbocation. From either side, it can attack on the carbocation, leads to a equimolar mixture of the products, where one product will have same configuration as the reactant configuration, and this happens when the nucleophile attacks on the same side as the halide ion left. Okay, that means from the same side where the carbon halogen bond is present. And the second product will be having opposite configuration from the reactant. It does occur when the nucleophile attacks from the opposite side to the halide ion left. That means from the opposite side of carbon halogen bond. Let's see, or let's understand this factor using an example. So this is your compound CH3, CHBr, CH2, CH3, your 2-bromobutene. Okay. In the first step, carbocation makes or carbocation forms after the removal of this leaving group, bromide ion. This is a slower step, and the carbocation you got is sp2 hybridized and also planar. So the incoming nucleophile, which in case is hydroxyl ion, can attack from both the sides on the carbocation. You can see in this picture, right? So OH minus can attack from here or here in both sides because it is a planar molecule, sp2 hybridized, and nucleophile can attack from at the same side as halide ion left or from the opposite side to halide ion left. If it is attacking from the opposite side to the halide ion left, you will get this structure of butane 2-ol, where you can see the configuration is opposite to that of the reactant, alkyl halide, right? Meanwhile, if the hydroxyl group, if the nucleophile attacks on the same side as halide ion left, then you will get this configuration of butane 2-ol, and this configuration is same as the configuration of alkyl halide as reactant. Okay, so you are getting an equimolar mixture of these two products, one is having same configuration as reactant and the other is having opposite configuration of reactant. And this equimolar mixture containing, or you can say the equimolar mixture of enantiomers is actually racemization, right? Or racemic mixture. So in the SN1 reaction, the racemization is occurring. Now, if we talk about the another type of nucleophilic substitution reaction, that is substitution nucleophilic biomolecular reaction, SN2 reaction. So, in this reaction, it happens via single step. So, this is a single step reaction. The carbocation formation will not happen. Actually, in a single step, the carbon halogen bond breaks and the incoming nucleophile and carbon bond makes. So, the product you got have inverted configuration compared to the reactant. Nucleophile will attack from the side opposite to the living halide ion. Okay, so in the SN1, you are getting equimolar mixture of two products. One is having same configuration as reactant, the another is having inverted configuration as the reactant, opposite configuration. But in the SN2 reaction, the product you got has only inverted configuration compared to the reactant. That means that nucleophile has attacked from the opposite side to the living halide ion. SN2 reactions of optically active halides causes inversion. So inversion happens in the SN2 reaction. Let's understand it using an example. So we have this molecule of alkyl halide on which the nucleophile is attacking. Okay. So this is a single step reaction. So in this step, a transition state forms here in between where the carbon here at which the halide ion is present, that carbon is bonding with the 5 substituents at the same time. That means that carbon is making 5 bonds simultaneously. That is a transition state, very unstable. And in that transition state, the making or the formation of carbon and nucleophile bond is happening and the breaking of carbon and halide ion is happening. Okay, and finally you will get a final product as alcohol after the bonding of the nucleophile and the carbon after the removal of halide ion or living halide group. Okay, so SN2 reaction is a single step reaction, and in this reaction the nucleophile attack from the opposite side to the living halide ion causes the inversion of configuration of the product as comparatively to the reactant. You can see both the configuration of reactant and the product. Reactant and product configuration are opposite, inverted. So conclusion is that racemization occurs in the SN1 reaction and inversion occurs in the SN2 reaction. Hence, we can check one by one the statements given, the statements in the given options. So the A statement was retention occurs in SN1 and inversion occurs in SN2. This is incorrect because we just have seen that inversion is occurring in the SN2, but retention is not occurring in the SN1. The B statement was racemization occurs in SN1 and retention occurs in SN2. This is also incorrect due to this given statement that retention occurs in SN2. Okay, this is incorrect. C statement says racemization occurs in both SN1 and SN2 reaction. This is also absolutely incorrect. The D option statement says racemization occurs in SN1 and inversion occurs in SN2, and this is very correct information or correct statement. So the correct option is D. The correct answer is D option. Let's see our next question. Question is, alkyl halide is converted into alkyl isocyanide by reaction with which reagent from the given options? So you have to identify the reagent which on reacting with alkyl halide convert it to an alkyl isocyanide. Name is very important, isocyanide. Cyanide and isocyanide, there is some difference. Okay. Options are sodium cyanide, ammonium cyanide, potassium cyanide, or silver cyanide. So this question has correct answer as option D, that is silver cyanide. The reaction for alkyl halide with silver cyanide is as follows. So when an alkyl halide reacts with silver cyanide, what will happen? This halide group will leave or replaced by the cyanide group, and you will get alkyl isocyanide as your major product plus silver halide will be your byproduct. Okay. Now you can observe that this CN is connecting with this alkyl group via nitrogen, not by carbon. Why is it so? Let's see that. So AgCN is a covalent molecule. It is not ionic, it is a covalent molecule, due to which it does not dissociate into silver positive and cyanide ion. And due to that, the attack will possible only from the nitrogen lone pair. So how, if the AgCN is not dissociate into ions, then how it is going to bind with the alkyl group? So it will bind to the alkyl group from the nitrogen lone pairs. Lone pairs present on the nitrogen will bind to the alkyl group and form isocyanide when it reacts with alkyl halide. Other given molecules in the options are sodium cyanide, ammonium cyanide, and potassium cyanide. If you talk about them, they are ionic molecules. What does that mean? That they will dissociate into their respective cations and anion will be Cn negative. That means the anion Cn negative here is an ambidentate nucleophile, right? That means it can attack from both the sides, from carbon or nitrogen to the alkyl group. If it attacks from the carbon-carbon bond formed between alkyl and the carbon of cyanide group is stronger than the carbon-nitrogen bond if the attack happens from the nitrogen, from the cyanide to the alkyl. So, because carbon-carbon bond is stronger comparatively to the carbon-nitrogen bond, attack will happen from the carbon atom of cyanide group. And hence, it will form cyanide molecule when it reacts with alkyl halide. Okay, so these ionic molecules when react with alkyl halide form cyanide as a product, not isocyanide. Hence, the only correct option is option D, that is AgCN, because this is only the product, or you can say this is only the reagent, which when reacts on alkyl halides converted to alkyl isocyanide. It gives isocyanide, not cyanide. Okay, let's see the next question. Question is the correct order of reactivity in the electrophilic substitution reaction of the following compounds is. So we have given 4 different compounds. You have to tell the order of reactivity of these compounds towards electrophilic substitution reaction. The first compound is simple benzene ring. The second compound is a toluene. Third compound is chlorobenzene. And fourth compound is nitrobenzene. So options are, the order of reactivity towards electrophilic substitution is highest for second molecule, then for third, then for first, and least for fourth. Or it is highest for fourth, then third, then second, then first. Or it is highest for first, then second, then third, then fourth. Or it is highest for second, then first, then third, then fourth. So the correct answer for this question is option D. That means the order where second molecule is having highest reactivity. After it comes the first molecule, then third, and then fourth molecule. So let's understand the electrophilic substitution reaction, that is ESR. In the electrophilic substitution reaction, attack of electrophile happens. E positive will attack on the electron-rich benzene ring. So substitution and attack happens via the substitution of hydrogen positive from the aromatic ring, that is benzene ring. So what will happen? Hydrogen positive from the benzene ring substitute and the electrophile gets attached at its place. And formation of sigma complex happens. So when electrophile attacks on the carbon of benzene ring, a sigma complex formed after the sigma bond formed between electrophile and carbon. If your sigma complex formation, if your sigma complex formed is more stable, the electrophilic substitution reaction rate will be higher. This is your sigma complex formed after the bonding with carbon of electrophile. So when electrophile bonds with carbon of this benzene ring, this forms a sigma complex. It is you can say electron deficient complex. Okay. So this is the sigma complex. You can see this positive charge is distributed all over the benzene ring. Okay. So this is the sigma complex. And sigma complex, if you want to stable, it will be stabilized by resonance, because resonance is the factor shown by benzene ring. Okay. So sigma complex can be stabilized by the resonance. Also, if any electron donating group is present on the benzene ring, it will stabilize this sigma complex by showing plus I, plus R, and plus M effect. That means plus inductive, plus resonance, plus mesomeric effect. And the sigma complex will destabilized by the electron withdrawing group, because it is already electron deficient. If any electron withdrawing group is present on the benzene, it will withdraw the electrons from the benzene ring, makes it destable. So it will destabilize by minus I, minus R, and minus M effect shown by the electron withdrawing group. If we talk about the molecule first is a simple benzene ring, right? Molecule second, it is, so benzene ring in the molecule second is substituted with a methyl group, that is CH3. And the CH3 is, or you can say that molecule, the second molecule is also known as methyl benzene or toluene. CH3 present as a substituent is electron donating group. What does that mean? It will donate the electron towards the benzene ring, increase its electron density through plus I effect and plus H effect. That means plus I means its electron donating nature, and plus H effect, that means plus hyperconjugation effect. The sigma bond between carbon hydrogen atom donates that sharing electrons. Okay, CH sigma bond electrons will be shared towards the adjacent benzene ring. So through both these effects, plus I and plus H, the CH3, the electron donating group, will increase the electron density of the benzene ring, and this will stabilize the sigma complex after the attachment or after the bonding of electrophile with it. Sigma complex becomes stable, that means the ESR rate will become or will increase as compared to simple benzene, because at the benzene no electron donating group is present, not any kind of group is present. And if there is an electron donating group present on the benzene, it is kind of stabilizing the sigma complex, increasing the rate of electrophilic substitution reaction shown by it as compared to the benzene. So if we talk about the molecule third, which is in which benzene ring is substituted with chlorine group. So this compound is known as chlorobenzene. Chlorine present on the benzene is electron withdrawing group. That means it will withdraw the electron from the benzene ring, decreases its electron density through minus I effect, and increasing the electron density through plus R effect. Okay, so minus I effect shown by chlorine, that means it will withdraw the electrons of the benzene ring towards itself due to its electronegativity, higher electronegativity, and also it will increase the electron density by plus R, by plus resonance effect, because its lone pairs, the chlorine lone pairs, will participate in the resonance of the benzene ring, increases its electron density through the plus R effect of chlorine. But overall, it is taking as an electron withdrawing group, because minus I effect will dominate over the plus R effect. And due to its nature of electron withdrawing group, it will destabilize the sigma complex, due to which the rate of ESR will decrease as compared to the benzene. Okay, so benzene is now between of you can say toluene and chlorobenzene. Okay. Now if we talk about the molecule fourth, the substituent is nitro group, and it is also known as nitrobenzene. The fourth molecule is nitrobenzene. Nitro group is an electron withdrawing group. Okay, so what will happen? It will withdraw the electrons, decreases the electron density through minus I and minus R effect. and this will highly electron withdrawing group. Okay, this is a important, or this is again most effective electron withdrawing group, the nitro group, due to its electron withdrawing nature, it will destabilize the sigma complex formed, due to which the ESR rate will decrease as compared to the benzene. So now we have two molecules, the molecule third and fourth, which is having electron withdrawing group as a substituent on the benzene ring, and it is destabilizing the sigma complex and decreasing the rate of ESR. So now we will compare between the molecules third and molecule fourth, because both are showing the same nature, right? So both the molecules is destabilizing the sigma complex intermediate. Chlorine atom present in the third molecule is destabilize the sigma complex by minus I effect, but also it is stabilizing by plus R effect. This is the factor, right? That chlorine atom is, yes, it is destabilizing by minus I effect, the sigma complex, but it is also stabilizing the intermediate by plus R effect due to the presence of lone pair participation of the chlorine in the resonance. But if you talk about the NO2 electron withdrawing group, it is only destabilizing by both minus I and minus R effect. So overall, the NO2 group, the nitro group, is more electron withdrawing group than the chlorine atom, due to which the rate of electrophilic substitution reaction in the nitrobenzene is lesser than the chlorobenzene, because chlorine destabilizing by minus I, but also it is stabilizing by plus R. So rate will slightly increase in the chlorobenzene comparatively to the nitrobenzene. So conclusion is that methyl substituent stabilizing the intermediate, the sigma complex. So rate of toluene towards the electrophilic substitution is highest. And NO2 destabilize the intermediate due to its electron withdrawing nature. So the rate of nitrobenzene towards electrophilic substitution is lowest. So your order of reaction will be highest for the second molecule, then comes the benzene, then the third molecule, that is chlorobenzene, and then least will be for nitrobenzene. So the correct answer is option D. Let's see the next question. The question is, which among the following halides will not show SN1 reaction? So we have given 4 molecules. The first is CH2 double bond CH single bond CH2 Cl. This is, and you can say haloalkene. Okay. Second molecule is CH3 CH double bond CH Cl. Third molecule is benzene ring over which CH2 Cl is present. And fourth molecule is CH3 CHCl CH3. You have to choose the most appropriate answer from the options given below, and options are, so what you have to choose? You have to choose that among the given halides, okay, or you can say alkyl halides, or you can say haloalkenes or benzylic halides, which one will not show SN1 reaction? Okay, so the options are first, second and fourth molecule only, first and second molecule only, second and third molecules only, or second molecule only. So your correct answer for this question is option D. Let's talk about the SN1 reaction first, because we are asking that which will not show SN1 reaction. SN1 is a two-step reaction, and this reaction will proceed via the formation of carbocation, which happens in the first step, which is lower step, which is rate determining step. So stability of carbocation is a rate determining step in the SN1 reaction. That means more the stability of carbocation, more will be the rate of your reaction. So order of reaction in different types of alkyl halides or halides are highest for benzylic halide, then for allylic halide, then tertiary halide, then secondary halide, and least is for primary halide, because primary halide will give you primary carbocation, which is least stable carbocation. Secondary halide will give you secondary carbocation, which is more stable than the primary carbocation, and such like that we have this order of reaction shown by various halides. Now if we talk about the molecules one by one, let's take the first molecule. Now, in the first molecule, how the formation of carbocation happens. So, you have given this molecule CH2 double bond CH2Cl. It will convert to an allylic carbocation after the removal of this halide ion, and this positive charge will come on this carbon. You got allylic carbocation. That means positive charge on the carbon, which is connecting with sp2 hybridized carbon atom. So you are getting a allylic carbocation in the first molecule case. This carbocation is stabilized by resonance. So this structure of carbocation is equivalent to this structure after the charge stabilization by resonance. Okay, so this double bond electrons will be shifted from here to this. Here on this carbon, this positive charge will shift it to this carbon then. And you will get this equivalent structure of this carbocation. So the stability of carbocation is by the resonance. That means carbocation is stable or it is stabilizing by resonance. That means this molecule will favor the SN1 reaction, because SN1 reaction, in the SN1 reaction, stability of carbocation is the key factor. Now, for the second molecule, how the formation of carbocation happens. So, the second molecule, this leaving group, that is halide ion, that is chloride ion, will left from here, and positive charge will come on this carbon. So, you got vinylic carbocation. That means positive charge on the carbon, which is only sp2 hybridized. Okay. So, you are getting a vinylic carbocation, which is very unstable. Why? Because positive charge is present on an sp2 hybridized carbon, making this carbocation unstable. This is, you can say, this is very rare, right? That positive charge comes on this double bonded carbon, because this carbocation is actually very unstable. Hence, what the stability of carbocation is saying, that it or this molecule does not favor SN1 reaction. If we talk about the molecule third, in the third molecule, so the formation of carbocation happens after the leaving of the leaving group, that is chloride ion. So after this chloride ion will be removed from here, the positive charge comes on this carbon directly connecting with benzene. So you are getting a benzylic carbocation. Okay, so you are getting a benzylic carbocation in the third molecule case. Benzylic carbocation is very stable carbocation. We just have seen the order of reaction of different halides, remember? And in that order, benzylic halides are most reactive towards the SN1 reaction, or towards, you can say, it is most stable carbocation given. Okay, so benzylic carbocation is actually very stable carbocation, due to which the carbocation, okay, and in this case the carbocation is stabilized by the resonance shown by the benzene ring. So this positive charge is stabilized by the resonance. How? So you can see in this different figures which are equivalent to each other. So you have this positive charge. For the stabilization, this double bond electron pairs will move from here to here. A partial double bond character arises between the CH2 and the carbon of benzene ring, and the positive charge shifted on this carbon. Now the next double bond electrons will shifted to here, and this positive charge will come from here to this carbon, the para carbon. So you get this structure, the double bond from here shifted to this. Okay. Now what will happen? For the stabilization of this positive charge, this double bond sharing electrons will come here. This positive charge will go at this carbon, and you got this structure. Now again, this you can say partial double bond will break, and these electrons will move to this carbon, and this positive charge again goes to CH2, and you got this structure. Okay, so these are the equivalent structures showing the resonance happening in this carbocation, benzylic carbocation. So this benzylic carbocation is very stable, stabilizing by resonance shown by the benzene ring. Hence, this molecule third will favor SN1 reaction. Now for the fourth molecule, CH3, CHCl, CH3, how the carbocation form? So after removing this chlorine, the positive charge comes on the center carbon, and you got CH3, CH positive, CH3 as a carbocation. Now this is a secondary carbocation. You can see the positive charge is on the carbon which is attaching with other two carbons. So this is secondary carbocation, and this carbocation will also be stabilized by inductive effect, plus I effect. Okay, so methyl group shows plus I effect, electron donating effect, through which this you can say this carbocation will get stabilized. So positive charge will be stabilized by the electron donating by the plus I effect shown by these two methyl groups. And also this carbocation is stabilized by hyperconjugation effect, that is plus H effect. So the sigma bond between carbon and hydrogen will share the electrons to this carbon and stabilize this positive charge present over the carbon. Okay. So this carbocation is stabilized by plus I effect and plus H effect both. How? So you can see that this sigma bond between carbon and hydrogen showing positive hyperconjugation effect, and these electron pair are shifting to this carbon. The positive charge will be removed from this carbon and double bond came for the stabilization of the carbocation, and H positive will be removed. So, because this carbocation is again stable and stabilizing by plus I and plus H effect, this molecule will also favor SN1 reaction. So, the conclusion is, the question asked was which of the following halide will not show SN1 reaction. So, from all the molecules, the vinylic carbocation molecule is only the one which does not give SN1 reaction. Hence, your correct option is the D option. Okay, let's see the next question. Question is giving, and question in the question we have given different you can say cycle of reaction. Okay, or different various steps of a reaction. First, we are taking a reactant bromoethyl C2H5Br. We are reacting it with alcoholic KOH and getting A product. Then A is reacting with bromine molecule in the presence of CCl4. We are getting B product. B is reacting with potassium cyanide in the excess amount and getting C product. And C, when it is reacting with H3O positive in the excess, getting we are getting D product. The final product D is an acid, and you have to name that acid D formed in this reaction. Options are gluconic acid, succinic acid, oxalic acid, or malonic acid. So for this question, let's see, we have given the reaction where 4 steps are involved. We are getting 4 products, A, B, C, D. 4 steps are involved. Step 1 is the reaction of ethyl bromide with alcoholic KOH, and when it is reacting, we are getting A product in the step 1. Step 2 include the reaction of compound A with the bromine molecule in presence of CCl4, and you are getting a product B in the step 2. Step 3 includes the reaction of B with the KCN, which is in excess amount, and you are getting the product C in the step 3. Now in the step 4, hydrolysis of compound C is happening in presence of H2O positive in excess amount, and you are getting a product D in the 4th step, and it is already given that D product is an acid. So the step 1, where the reaction is happening and you are getting a molecule A, reaction of alkyl bromide in the presence of alcoholic KOH is a dehydrohalogenation reaction. Okay, that means one hydrogen and one bromine. That means one halogen and one hydrogen will be removed, will be substituted from your alkyl halide after the reaction of alkyl halide with alcoholic KOH. This reaction is also known as beta elimination. That means beta hydrogen will be removed. The molecule A you are getting will be an alkene, because this process also involves the removal of hydrogen. So you will get alkene. That is, from ethyl bromide you are getting ethene as the major product after the reaction of alcoholic KOH with ethyl bromide. So the A molecule, the A product is ethene. Step 2, includes the formation of molecule B. So the reaction of alkene, because A is alkene. Alkene, when reacts with bromine molecule in presence of CCl4, follows an addition reaction. So the bromine will going to add upon in the alkene molecule. And the molecule B you are getting is a vicinal dihalide. So ethene reacts with bromine in presence of CCl4, giving us 1,2-diabromoethane. Okay. 1,2-diabromoethane, and this is vicinal dihalide polyhalogen compound. The two bromine atoms are attached with the adjacent carbons. So molecule B is 1,2-diabromoethane. Step 3 is formation of the molecule C, where vicinal dihalide, which is B, is reacting with potassium cyanide in the excess amount, and now this is following a nucleophilic substitution reaction. The cyanide from the potassium cyanide, because potassium cyanide is an ionic compound, it will dissociate into K positive and Cn negative. Cn negative will act as a nucleophile, and Cn negative is our ambidentate nucleophile. We have talked about it. That means it can bind to alkyl via carbon and nitrogen both. So attack can happen from both carbon or nitrogen. If carbon-carbon bond form between the alkyl and the cyanide group, it will be stronger bond as compared to the carbon-nitrogen bond between alkyl and cyanide group. Hence, the attack will happen from carbon position, forming carbon-carbon strong bond. Because cyanide is present in the excess, the KCN is in excess. So, both the bromide ion in the vicinal dihalide was substituted by cyanide ion, and you will get the molecule C, which is diacyanose compound. So 1,2-diabromoethane, when reacts with excess of potassium cyanide, you will get butane 1,4-dianitrile. So C molecule is butane 1,4-dianitrile. In the step 4, we are getting the molecule D. So in the presence of H3O positive, the diacyano compound we just have got, that is C molecule. So from the C molecule, both cyano group gets hydrolyzed because H3O positive is in excess. And after the hydrolysis, both cyano groups will convert it to carboxylic acid, that is COOH. So butane 1,4-dianitrile reacts with H3O positive in excess, convert to succinic acid, COOH, CH2, CH2, COOH. So your D compound, your D molecule is an acid named succinic acid. Okay, so D molecule is a succinic acid, and the compound D is also known as succinic acid, and hence the correct option is B, that the name of the acid D you are getting in this 4-step reaction is succinic acid. So option B is the correct answer. Okay, thank you so much. That's all for today's chemistry session. Thank you.